Okay. So 4.1 is going to be talking about things called probability distribution functions for a discrete random variable. Okay, pretty wordy. A lot difficult to say than actually do this. So this is actually a pretty easy concept. But what we're trying to do is start to use our probability knowledge that we gained in the last chapter with scenarios that are really authentic, real life, things that are actually done. Okay, we're not really going to in real life be concerned of and be able to use in application the probability that I pull a red card out of a deck of cards given I've already pulled a black one out. Okay, that's in real life not much of a use to that. Okay, but we're going to start seeing more and more questions that do have a particular application, and you'll start to maybe see the real use of statistics here. Okay, but we need to revisit a couple vocabulary words that we saw in chapter 1 and chapter 2. First one was discrete data. If you remember, the word discrete refers to the ability to count something. Okay, so we're not going to have I don't want to say this. We're not going to have. How can I word this the best way? Because I want to say decimals, okay? But we could potentially have decimals the way it's structured, okay? But discrete data, I'll give you an example here in a moment, but discrete data says data that you can count, like people in a room, people with an illness, number of votes, that kind of thing, okay? But if we had, so let's say we're doing a study where we ask people that, to the nearest hour or to the nearest half hour, what is the amount of time you spend studying in a week? Okay, so our results could be 0.5, 1, 1.5, 2, 2.5, 3. Does that kind of make sense? And then basically those people would be categorized in those values. Those are decimal. Some of those are decimal, right? But they would still be considered discrete because I can count how many people were in that column or that category of 2.5 or 1.5 or whatever. Okay, so I don't want to say that everything that has a decimal cannot be classified as discrete, but the idea is that it's countable. That's what we're looking for with a discrete data. If you guys read, so visually, we have discrete random variables and we have continuous random variables. I want to show you the difference of them visually, okay? So discrete is the idea that my pieces of data might be things like 1, 2, 3, 4, 5. Those are countable, okay? Continuous means that my data can take on any value between two endpoints, okay? So if I kind of look at that, okay, if I look at the discrete random variable between 1 and 10, I can only take on the values of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a finite amount of it, okay? If I think about all the values that my continuous random variable can take on between 1 and 10, there are a lot more, right? Does that kind of make sense? So continuous is, and a lot of times continuous we're talking about being things that you measure. Think about taking like if I take like a 5-gallon bucket and I set it outside for a month, okay? And then I go out at that 30th day and I measure the amount of precipitation that is in that bucket, okay? I can have anywhere between 0 and 5 gallons, right? Okay? I'm not going to have 0 gallons, 1 gallon, 2 gallons, 3 gallons, 4 gallons, or 5 gallons. And it's actually going to be very rare that I would have exactly 1 gallon or exactly 2 gallons or something like that, right? But I'm probably going to have somewhere in between any one of those. And the value that then can take on would be considered a continuous variable. Does that make sense to everybody? If we're talking about our measurements, our heights, our weights, that kind of thing, think about like the shortest person compared to the tallest person in the world. You got your endpoints now of your interval, and everybody else is going to fall somewhere in between. But you're not going to be just 5 foot. You're not gonna be 5 foot 1 inch. Okay, you're somewhere between. You know, especially using the idea of how our measuring tool, how precise our measuring tool is. You're not going to fall on a discrete value. Okay, does that make sense? A lot of it's usually pretty easy to determine whether something is discrete or continuous. I always try to say, does it meet the qualifications to be discrete, yes or no? And if the answer is no, then obviously it falls in the category of being continuous. Okay, and it gives you a better idea than what are continuous variables. But a random variable represents a numerical value associated with each outcome of a probability experiment. Okay. So it's a variable whose values are determined by chance. So random variable, I don't know the definition, it's very insightful. So we'll see some examples here that maybe make it a little bit more comfortable understanding of that word. But notation-wise, when we talk about a random variable, probably 99% of the time you're going to see capital X being the label that or the notation that we use for a random variable. And when they say capital X, so you're going to write your random variable in words. You're going to express it in words. And then use lowercase letters. Okay, so if I use capital X to identify my random variable, then I use a lowercase letter to actually represent the actual values that variable can take on. Okay, so if I use capital X, I then use lowercase x. If I use capital Y, I'll use lowercase y. So if X is a random variable, then X is written in words and lowercase x is given as a number. So here's an example. If we were to toss a coin 3 times and I ask what is the number of heads that you can get when you do that, okay? We say capital X equals the number of heads you get when you toss a fair coin 3 times, okay? That is the random variable. Okay, now it's a discrete random variable because I can only get 0 heads, 1 head, 2 head. I can't get like 1.5 heads. Does that make sense? Okay, so I'm only getting those whole number results, so this is going to be discrete. I'm counting them. Okay, now the question is, how do I decide what the values that the random variable takes on? Well, going off of what we talked about yesterday and the day before, in order to do this, we should probably construct a tree diagram. Okay, so I'm going to make this tree diagram flow just because of my space flow this way. So my tree diagram, and I'm pretty bad at organizing these because I always run out of room. Always pack things in tight. So I could have heads or tails on the first toss, right? The second toss, if I got heads the first one, I could have heads or tails the second one, right? If I got tails on the first toss, could I have also had heads or tails on the second? That makes sense? And then we got this last one. If I go heads, heads, I could have heads, tails. If I go heads, tails, it could have been heads, tails. And then we get this final one, heads, tails again. So this was the first toss. This was the second toss. This is the third toss. So when I talk about my outcomes, my sample space, it's heads, heads, heads. That would be one configuration of results. I could have heads, heads, tails. Heads, heads, tails. We can go heads, tails, heads. Or heads, tails, tails. Okay, so that's going down this branch to that one, and then finally those two. And then if we start with tails, we could go tails again, and tails again. We can go tails, tails, heads. We can go tails, heads, heads, and tails, heads, tails. Okay, so again, if you start with that, all we're doing is making sure that we follow down whatever pathway you want, but you're going to end at one of these. So if I do this, so every one of these, so if I do that in purple and then I follow one in blue, each time I do this, I should end up at one of these final conclusions, and then I just trace back, okay, what did I highlight in that green one? And I label those. Okay, so that's how I get my 8 sample space, or 8 outcomes in my sample space. Okay, so then the random variable takes on the values that are attached to what we define our random variable to be. The number of heads that you can get when you toss a fair coin 3 times. Can you get 3 heads? So that's why X could be 3. Can you get 2 heads? So that's why I've got 2 there. Can I get, so that's 2 heads again. Here's 1 head. And then in this situation, there would be no heads, right? So if you were to do this experiment over and over and over and over again, okay, the different types of outcomes you could get with this random variable. You could get 0 heads, 1 head, 2 heads, or 3 heads when you do this. Okay, so it says X is in words and lowercase x is in numbers. Okay, it says in this example, X values are countable, meaning they're discrete, 0, 1, 2, 3. How many heads you have is a discrete random variable here. All right, so when we're dealing with, so those are the types of scenarios that we're going to be dealing with here right now. Okay, eventually, once we learn discrete random variables, we'll do a similar procedure for continuous random variables. Okay, we'll be able to draw the like the contrast between those two. Once we have that, once we are able to identify what our random variable is, and we're also able to identify the values that it can take on, we then like to create what we call a probability distribution function. Okay, and like I said, it's wordy, but basically all it is a table that shows you the probability of each of those random variables. Okay, so it says it lists each possible value the random variable can assume together with its probability. Okay, it says a discrete probability distribution must satisfy the following conditions. All right, so the probability of each value. Okay, so when it says the probability of each value, that is talking about all those x's that we had. So x is equal to, we had 0, 1, 2, or 3. Okay, so the probability that we get 0 heads will be between 0 and 1. Okay, inclusive. Okay, meaning you could have 0 chances of that happening, or it could be certain. Okay, now if it was certain, that's kind of a boring thing. An example of like a boring probability distribution function that would have a probability of 1 would be, let's say I put Lucas's name in a hat, and his is the only name I put in the hat, and I ask what is the probability that I reach in there and I pull out Lucas's name, make a probability distribution function over that. That's pretty boring because the probability that I'm going to pick his name out and his is the only one in there would be 1, right? There'd be no other events in there, no other outcomes. It's boring. So usually we don't see the distribution, the individual x's totaling or being 1 themselves. But it's not rare for a certain probability to be 0. Okay. The other criteria is that the sum of all probabilities is 1, and that's something that we've known for a while, right? Okay. So some of your questions in your homework, they'll actually give you a probability distribution table, and they'll say, "Is this a valid probability distribution table?" Well, you need to go through each p of x that they give you and make sure that they are all between 0 and 1. Check that off. If they are, that's good. Then you add them all up, and if they sum to 1, then you're good, and you got a probability distribution function. If not, if one of those is violated, then you do not have a probability distribution function. Okay, so we'll create a couple of these. I don't think this is going to be something that's very taxing to you. The way that we do this, there's 4 steps. I don't know if you ever make one of these that you really think about all 4 steps here. It's just kind of inherent that you construct your table pretty easily here. But you make a frequency distribution for the possible outcomes. So kind of like what we did with that sample space. Those are our possible outcomes. And we would make a table of those representing, okay, this is how many times out of this sample space that we can get 0 heads. It'd be 1, right? 1 out of 8 total. How many times can I get, 1 head? Okay, and then we will go count through those 8 and see how many have just 1 H in them. And then we can do the same thing with 2 H's. How many of them have 2 H all the way through? And 3. So we can do that. We can create a frequency distribution table. Then you're going to find the sum of the frequencies, and that's usually pretty easy to do. Okay, just add up all the, so up here, if we're doing this one, we add all those up and we get 8. Okay. Then you're going to find the probabilities of each possible outcome by dividing frequency by the sum of frequencies. So that, if you remember, that is just finding the relative frequency. You're going to take the frequency of the column that you're in or the event that you're talking about and divide by how many total that you have. And the last thing is just to check to make sure that you have all individual probabilities between 0 and 1 and then that they sum to 1. Okay? So something that, if we want to go back through and use this information here, use this example. Basically what you're going to do is you're going to say, and these can be vertical or horizontal, you're going to have an X row or column, in this case a column, and you're going to have a P of X, okay, which stands for the probability of that event. So this is my random variable. So in this column, the values of my random variable go in that column. So 0, 1, 2, and 3 were the potential values for my random variable, right? And now we just determine, okay, of these 8, how many of those had 0 heads? There's just the 1 out of 8, right? So usually, and it's not always, but usually we like to write our probability distribution functions with decimals. So 0.125 would be that probability. Okay. If we have just 1 head, okay, so going through here, there should be 3 that have just 1 head, right? So 3 out of 8, which is 0.375. The ones that have exactly 2 heads, so 1, there's 2, and there's 3, 0.375. And then 3 heads, we're just back to this one here, right? Okay, so 0.125 again. Okay. The idea is that each one of these probabilities is between 0 and 1. Okay, and if you add those up, you get 1. So the sum of your P of X's is indeed 1 there. And that's a probability distribution function. Is that pretty easy to do? Okay, so I got another example down here. Says an industrial, so here's where, flipping a coin again, not a real applicable scenario. Okay, a real life scenario, okay? Here's where you start to see maybe our focus or redirect our attention on like medical survey or medical studies, financial studies, that type of research, and the statistics that aligns with those fields. So here it says an industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Okay, it says each individual was given a score from 1 to 5, where 1 was extremely passive and 5 was extremely aggressive. Okay, so the score of 3 indicated neither trait. So the results are shown below. Construct a probability distribution for the random variable X, then graph the distribution using a histogram. Okay, so we've already got a frequency distribution over here, right? So remember, frequency distribution tells us how many times each one of those events was occurring, okay? If I'm talking about capital X, which is my discrete variable, okay, discrete random variable, the idea or the story here says that we're talking about the personality inventory test for passive-aggressive traits, right? Okay, so we would want to word this as somehow identify that X is representing the placement of a person on the scale for passive-aggressive traits. Okay, and on that scale, we were going from 1 to 2 to 3 to 4 to 5. Those are our options, right? Those are the values. Those are the individual discrete values that lowercase x can take on. They can take on 1, 2, 3, 4, or 5. Okay? So when looking at this, they're asking us, what is this over here is our probability distribution function. Okay? A lot of times they'll abbreviate it PDF. So we've got 24 people scored a 1, okay, out of 150 employees, right? So all we've got to do is 24 divided by 150, and we get 0.16. Okay, 33 people received a score of 2, so 22. 42 people received a score of 3, so 0.28. Yes?
Are they like searching for passive traits and aggressive traits, or passive aggressive traits?
Well, like this, so they're saying this person is passive.
Okay. So
this person is aggressive.
They're not saying they're passive aggressive.
Right. Passive because of the hyphen. Yeah. 4 would have been, so 30, at least that's the way I would interpret the question. 4 would be 30 out of 150, and then 21 out of 150, that goes to 0.14. Okay. Are each one of these between 0 and 1? If I add those all up, okay, 0.16 plus 0.22 plus 0.28 plus 0.2 plus 0.14, does that give me 1? So those two things check out. So we have a valid probability distribution function. Now, what's the purposes? It's organization of data at the moment, okay? And basically what it says is, if I then go to maybe in the next 1,000 people, using this data, I can say if I take 1,000 people, okay, I can assume that 1,000 times 0.16 is going to give me the total amount of people that are passive. If I take 0.22 times 1,000, it's going to give me the people that would have classified between neutral and passive. Does that make sense? And if I wanted to multiply by 0.14, I get the people that in that 1,000 that are going to be aggressive. So I can get an idea now off of another sample or another group of people, their breakdown based off of this information. Does that make sense? Okay. Now we can also, once we have this information, and this is where it becomes very useful, and we have a lot of different distributions that we can talk about. But this one, and we like to put them back in the histograms. Okay, now the histograms that we're going to make, I'm not going to hold you to the criteria that it was very involved, especially with continuous data, making a histogram where we find our classes and all that kind of stuff. It's really nice making a histogram with discrete data, because your x-axis just becomes the discrete variable. So 1, 2, 3, 4, and 5. Okay, and we're going to use, if you remember what we did with histograms, basically we're going to have a rectangle right there where we use that marker for 1 to be the midpoint of the histogram, or of the bar, of that category. Now, because x, or your random variable values, are along the x-axis, and then your probabilities are going to be on your y-axis. Okay, so in our probabilities here, our maximum is 0.28. So I'm going to come up here and say that that's 0.3 right there. This would be what, 0.15. Let's break this up into thirds then. So this would be 0.2, 0.25. Come down here and go 0.05 and 0.1. So just kind of, and your scale might be a little bit different than mine, which is fine, but your distribution shape will be identical. Okay, so you might be a little bit more detailed or less detailed on your y-axis, but when we're done, if we graph these things correctly, our distribution shape should be very, very similar. So if I go this 0.16, okay, so I'm going to guesstimate that height right there is 0.16, and we'll make my first bar for my histogram. A lot of times, they'll call these bends. Okay, I don't know if we mentioned that or talked about that when we were working on histograms. The next one at 2 is a height of 0.22, so maybe about right there. Three is at 0.28. 4 is back to 0.2. And then 5 is down back to 0.14, so about right there. And we've taken now our probability distribution function, transformed it into a histogram. And what does that histogram tell you? What kind of distribution shape do we have there? Okay, so it's symmetric. It may be bell curve. We'll talk about bell curve. We'll talk about later that our symmetric distributions are the ones that we're looking for, and that we would hope that we can maybe eventually kind of fill in that curve there, that bell curve to that. But symmetric is what we're looking for, and that's the information that we can get from creating this. Without this being transformed into a probability distribution function, into this second table, we can't arrive at this information. Okay, does that make sense? Now, if you were to make a histogram, a frequency histogram, okay, you would still have the same shape, but now this would be, instead of probabilities, it would be, the 24, the 33, the 42 would be frequencies, but the distribution would be the same. Okay, the shape of it would be the same. This one says a company tracks the number of sales new employees make each day during a 100-day probationary period. Says the results for one new employee are shown. Develop a probability distribution. All right, so the way you're going to do this is, so the sales per day is going to be our random variable, sales per day. That is the thing that can take on different values, okay? The values that it can take on are 0, 1, 2, 3, 4, 5, 6, or 7. So when I say X here, I'm going to then go 0, 1, 2, 3, 4, 5, 6, and it appears as though I didn't give you enough. Let's extend that a little bit, make your table a little bit bigger. And then P of X. Okay. I'm going to now, how do I find P of X? Well, I need to know the number of days. Okay. So let's go here. We're going to add those up. So we got 16 plus 19 plus 15. 21, 9, 8, and 2. So we get 100. And that might have been, was that discussed in the, okay. So that was discussed in the problem. So what we've got here is there were, out of those 100 days, there were 16 days that this guy sold nothing. Okay, 19 days that he sold one thing. Does that make sense? Okay, so going back through here and then filling in the probabilities, this should be pretty easy because it's out of 100. So 0.16, 0.19, 0.15, 0.21, 0.09, 0.1, 0.08, and 0.02. And just the criteria, okay, remember we had to have that each Each individual probability was between 0 and 1, right? That we've met. And then the sum of all of our probabilities has to equate to 1, and that we met. So this is a probability distribution function. We could then, once we have that data processed, we can then change that into a histogram and see maybe what kind of distribution this looks like. I would argue that that's probably, if you start looking at the data, most of your data is 0.16, 0.19, 0.15, 0.2. It's pretty large from 0 to 3, right? Okay, so he's making 0 to 3 sales the bulk of the time, and then 4, 5, 6, 7, he kind of tails off. So my tail is going to be to the right, correct? So if we put this into a distribution, into a histogram, is this going to be, is it going to be symmetric? Is it going to be skewed left, skewed right? If it tails off to the right, it's skewed right. So that we always go to where the tail tells us where we skew. Does that kind of make sense? Okay. 2 more. So taking the data, putting it into a probability distribution table is going to allow us then to go into specific types of distributions and be able to determine things like means, expected values, and standard deviations once it's organized in one of these distribution tables. There are different types of distributions. We can talk about uniform distributions. So if I give a test and you all get like a 85%, every single student gets 85%. That distribution would be uniform. It would look like a rectangle. Okay. We can talk about exponential distributions. We can talk about, you guys, normal distributions, which is the normal curve or the bell curve. Maybe somebody you have a little bit of experience with. We can talk about a lot of different types of scenarios that produce different distributions. One of the key distributions that we'll talk about later in this section, it probably won't, or chapter, it probably won't be until we get back from Thanksgiving, is what we call a binomial distribution, which is basically when we have 2 outcomes from an event that are possible. Okay, so like flipping a coin, there's only 2 outcomes that can happen from that, right? If I'm taking a test, I give you a test that has 20 questions on it, and they're all true and false. We could talk about what is the probability that I just go through there and maybe I get like a 85% just by putting true on all of them. We can talk about what that probability would be. Does that make sense? And that's called a binomial distribution because there's only 2, bi meaning 2, right? There's only 2 outcomes that can happen on a true or false test, true or false. Now we could do that using our probability techniques from chapter 3, but it is actually a little bit easier using this distribution. So section 4.1, getting us really the structure of our tables and probabilities, and then in the next couple sections we will actually dig in a little bit deeper to that.